So it turns out that a first-order filter is a pretty lousy approximation for a brick wall because, right, we already know a little bit more room here. We already know that for a first-order filter, it doesn't look like our ideal brick wall, right? It does this. Okay, and again, I'm going to plot it. I'll sketch over here on the left-hand side. My best approximation. Whoops, that's not so good. I can do better than that. Okay, so this is 1, 0.1, 0.01, right? Or 0 dB minus 20 dB minus 40 dB. Okay, so this is our first order filter. It turns out I can increase the order, right? So we talked about how the order is the order of the differential equation. I think I talked about second order systems at some point. So we can use a second order filter. So second order filter, well, it's going to be twice as steep. So it does this. So the first order filter has minus 20 dB per decade. For a second order filter, we got minus 40 dB per decade. Okay. Or we could have a third order filter. Let's use orange. I've used orange for a while. Minus 60 dB per decade. Okay, and so on and so forth, right? So every time we increase the order of the filter, we're going to make the cutoff steeper, okay? And well, what does it mean to be minus 40 dB per decade? Well, it means that at 10 times the cutoff frequency, we've got only 1% of the response. At 60 dB per decade, we're at, see if I can get this to sketch correctly. Here, right? We're at 0.0001 like this, minus 60 dB. See that in blue. Okay, so it's 0.1% at 10 times the cutoff frequency. So we'd like to use higher order filters they have a steeper cutoff. And it's basically minus 20 dB per decade times the order will be the slope of that cutoff. Okay, and so actually in the DC motor lab, I had you use a filter to filter the tachometer data, and we used a third order filter for that. So that was a fairly steep filter. And the program in MATLAB actually was a special filter design program to design what's called a Butterworth filter. And there what you do is you select the cutoff frequency that you want and the order of the filter, and it'll design the filter parameters for you. Okay. And I'll talk in just a little bit about there was something a little bit more subtle in that filter, because it actually turned out that that filter was for use on sampled data. Okay, I'm going to talk about that in just a second. But before I get to that, I want to talk about spectral analysis. And so let's suppose, for example, we were going to test a disk. So this is like relevant for disk drives and other things that have rotating disks as part of the setup. So here we've got a disk, and it's spinning around with rotation rate omega. And I'm showing here that I've got a detection laser, and so it can measure the height of this disk, okay? And so ideally, if this is like a perfect disk, this z of t would be a constant, okay? But in reality, what will happen is there's always going to be some imperfections. One thing that can happen is that the the disk may be misaligned to the rotation to this rotation axis. So when you clamp it on here, let's say it's got a shaft through here, and so there's always going to be some little imperfections in that clamp on the shaft, and so the disk is never going to be perfectly flat. And so as this thing spins around, this height will basically go up and down, and it'll go up and down exactly, it'll be up exactly 1 time per revolution and down 1 time per revolution. And so we'd expect to see basically a sinusoid from the height, basically z of t would sort of do this. And it was going to do this exactly at the rotation rate, okay? So it'll do it at exactly at omega. So this will have a characteristic frequency. So basically here, z of t is going to look like some amplitude z bar cosine omega t. So same as the spin speed. Okay. And then the other kind of thing can happen because there could be dynamic flutter of the disk, right? So this is like a flexural mode of the disk. And that won't necessarily, that flexural mode is really a property of the disk as a structure. So it's actually not going to depend on frequency. So this is like a characteristic frequency, and it's not going to be equal to omega, and it doesn't depend on omega. Right, so this is like the mode shape and the natural frequency of the disk, okay? It has a particular characteristic frequency. So I have some measurement data, it happens, from a rotating disk, and it's taken at 2 different rotation rates, okay? So I've got time history of the disk height measurement. Here, let me zoom in a little bit so it's a little bit more readable. Time history of disk height measurement, so this is basically my z of t here. There's time in seconds on the x-axis and z of t on the y-axis, and the first plot here was recorded at 3,000 RPM, and the second plot was recorded at 5,200 RPM. So these are actually like pretty typical spin speeds for disks that would be used for hard drives and data storage. And so if you look at these waveforms, well, you can see stuff that looks definitely looks periodic. It looks like a sine wave, but it's not at all obvious what information is in these waveforms, right? So we look at the time data, and it doesn't really tell us very much, right? So the time data is kind of mysterious. Now, in your MIDAC, right, this kind of data would be what you would record with the oscilloscope. But if you use the dynamic signal analyzer, right, you get a plot of the spectrum. And so what I did is I didn't have a MIDAC when I did this. Instead, I used what's called a fast Fourier transform, or the FFT, and that's the same thing as what the MIDAC is doing. So the MIDAC's dynamic signal analyzer is using a fast Fourier transform. It's using an FFT. And so let's look at this. So this is a plot of the height data, the z of t, but now I've taken the FFT of it, and so that gives me, instead of the plot of z versus time, now I've got the plot of this thing versus frequency. Okay, so it shows all the frequencies that are contained in that signal, and so there's what I guess I want you to observe. This is log amplitude, right? And so this is 10 to the 0 or 1, and then it's going down to like 10 to the minus 3. So this stuff here is basically the noise level of the measurement. This is like random noise, okay? And then there are some spikes, and these spikes correspond to sine waves. So if we, turns out that the fast Fourier transform, everybody knows hopefully what a Fourier series is. Fourier series is fitting a waveform with a series of sinusoids, and the fast Fourier transform is basically the same thing. It's calculating, basically, it gives me a peak that corresponds to the sine wave that matches something that's present in the data. So you see I've got a peak here that's somewhere around 1,000 hertz or 1 kilohertz. And I have 1, 2, maybe 3 lower frequency peaks that are sort of below 200 hertz. Okay, this was recorded at 3,000 RPM. And now it's not totally obvious to me what any of these things are, but I have data that's at 5,200 RPM. Now remember, what I'm looking for is I'm looking for the tilt signal will be a signal that where the frequency of that signal depends on the spin speed, and the flutter is independent of that. So let's look at the data at 5200 RPM, okay? And so now, well, I can look at this peak here. This one is unchanged. So basically, same F as the 3000 RPM data. But the stuff down here has changed a little bit. Okay, so let's look at this. I'll kind of flip back to the previous slide. Whoa! See now, like if you look at 3000 RPM, there's actually two peaks, but they're really closely spaced. And it's only when I increase the spin speed that I can see now that this peak has moved up in frequency. This guy is at the same frequency. He's at about 1 kilohertz, and so it's pretty safe to assume this guy is the disk flutter. So this is a flexural mode. Right, and I could look at it. Turns out there are books that have the handbook for a given thickness and radius and material of the disk. I can calculate where these flexural modes should be, and so I could look at, given the dimensions of this disk and the material it's made out, I could check and see whether this actually matches the right thing. But now let's look at the low frequency part of this, close up of the low frequency range. So what I did was I zoomed in, and I'm taking this part that I circled in red, and I zoomed in on it, and I plotted it for the 3000 RPM data and the 5200 RPM data. And if you look at it, okay, well, these don't match up very well, unfortunately, because the figures got moved. So, sorry, I'll draw my arrows like this. So this is a 60 hertz signal. This is at 120. And then this guy here is 50 hertz, right? So there's 50 hertz, so pay no attention to this. Okay, and I'll do the same thing over here. So this is 60 hertz. This is the 86.7. And there's 120. Okay? So if you look at these plots, what's common to them is that each of them has a signal at 60 hertz and a signal at 120. 60 hertz and 120. Okay? These are the kind of signals that you would typically see in the US whenever you do a measurement, because our AC line voltage is at 60 hertz. And so we'll get harmonics at 120, 180, 240 hertz. Okay. Basically everywhere that you have power, which is pretty much everywhere, you're going to see 60 hertz in measurements that you take. It's very hard to get rid of it. And you'll also see harmonics. And so usually when we're making measurements, like if we have the ability to somehow choose a frequency, then we would not put it at 60 hertz. We don't design things to have signals that it would be at 60 hertz because it's very hard to separate them from the AC line voltage. Now the signals that are different, though, you can see there's one signal that's at 50 hertz here, and then it's moved up to 86.7 hertz as I increase the spin speed. And so I did the calculations. So 3000 RPM, if I divide that by 60 seconds per minute, I get 50 rotations per second, which is 50 hertz. And similarly, 5200 RPM is 86.7 hertz. Okay? And so this signal, use maybe I'll use a highlighter for this, right? So this guy is the spindle signal. It's this guy here. Remember, that's from, like I said, it's because of the tilt of the disk on the spindle. And it turns out that the magnitude of these peaks is meaningful. So if you look at the, right, so this guy here, the disk flutter, I don't know what the units are here, but if we wanted to compare whether the magnitude of the flexing of the disk is similar to the tilt, well, we can just look at the magnitude of these peaks in the FFT. So this one's at this is like at 0.6 or so, 0.6 units, whatever those units are. And if I look over at these peaks here, you see that they're sort of similar, right? So this is 0.1, 0.2, 0.3, 0.4, 0.5. So I've got pretty comparable amplitude of the bending of the disk and the and the tilt of the disk on the mount. So if I cared about having it be very flat, I could say that